Greetings, everyone. The purpose of this video is to go over forms of valid and invalid arguments. And as we go through this, we'll see that these forms are based on ideas of conditional statements, contrapositives, converse, inverses, and also what we know about um, disjunctions or statements. So first thing I want to do is go over forms of valid arguments. The first one is what we call the law of detachment, and we'll start there on the left, where we can see the symbolic form for this. And for each one of these forms, what will our assumptions be, or the way we'll read these, is that we're given our premises as these first two lines, so those things are true. And then down here, what we're ended up with is some sort of a true conclusion based on those premises. So the first set of premises is that P implies Q is true. And if P is true, then we can conclude, therefore, that Q is also true. Okay, which hopefully makes sense because in a conditional statement, if the first part is true, then in order for the entire statement to be true, that means the second part also needs to be true. So let's look at an example of this. So over there on the right, we have our P implies Q, that if the battery is dead, the cell phone will not work. So that's our form P implies Q. So if the battery is dead as P, the cell phone will not work. That's Q. So again, we assume that's true. And then we also assume that P, the battery is dead, is true. And so therefore we can conclude Q, that the cell phone will not work. So that is the law of detachment. The next is what we call the law of contraposition. And so if you remember, this will be based on the fact that if the conditional statement is true, then the contrapositive is also true. So we again start with the symbolic representation and start with our premises there. So our first premise is that P implies Q is true. So just like the previous one, the conditional is true. This time we're going to assume that not Q is true. Okay, so the second part of the conditional is not true. And so therefore we can assume that not P is true. And again, that's because if P implies Q is true, then we know that the contrapositive, which is not Q, implies not P is true. So an example of this, given the conditional, if I practice, then I will improve. So that's our P implies Q there. I did not improve, so we see that that's the negation of the second part, the not Q, and so therefore we conclude I did not practice or not P. Okay, so that's the law of contraposition. Two more forms of valid arguments. The first there, the law of syllogism, which this is one of my favorites because it's kind of like this idea that one implies two, two implies three, so one implies three. So again, starting with the symbolic representation there, we have that P implies Q is true, Q implies R is true, so we have two conditionals to start with. But notice that they are connected by the statement Q, right? Q appears in both, and is kind of the connector between the two. And so because of that, we can conclude that the first thing, P, implies the last thing, because we kind of bypass Q there. So we can conclude that P implies R is true. And so looking at an example of this, we're given over here that if you text while driving, then you are driving distracted. So that'll be our P implies Q. If you drive distracted, then you are endangering others. So we see that if you drive distracted being repeated. So that's our Q implies a third statement R, this one here. And so then based on our setup there, we have that P implies R. So if you text while driving, then you are endangering others. And then finally is our law of disjunctive syllogism. And you'll see here that we have two forms of this. We're really just changing the second premise in each. So for both, we start with the statement P or Q being true, so a disjunction. And then for the second part, we assume that one part of that is not true. Okay, so we assume maybe not P or not Q. And if you remember about how truth values work for or statements, in order for an or statement to be true, one part of the statement has to be true. And so if we have, as we do in each of these second premises, that one part is not true, then the only way that those premises work is if the other part is true. Okay? So again, let's look at an example of that. So we have that Natalie will take chemistry or biology as her required lab science. So here our P would be that she takes chemistry. Our Q would be that she takes biology. And then we're told that she did not take chemistry, so we have not P. And so because P is not true, that means that we must conclude that the other part of the or statement, Q, is true. So therefore she took biology. Okay, so with those in mind, let's look at some examples of given valid arguments or completing valid arguments. So first example there, we're given as premises, if a number is divisible by 6, then it is divisible by 2 or 3. So I see here that we're given a conditional, so we have P being the number divisible by 6, Q being it's divisible by 2 or 3, where P implying Q. And then we're told that it is not divisible by 2 or 3, which means that the second part of the conditional, Q, is not true. So I see that our premises are P implies Q and not Q. So what that tells me, if we look back at that list that we just went over, that here we have an example of the law of contraposition. Okay. And the law of contraposition tells us that, again, if we have the P implies Q true, not Q true, then our conclusion must be P, right? Or excuse me, not P, which is, in this case, would be that the number is not divisible by 6. Okay, so the negation of P there. Let's take a look at the second one. Again, we look at our premises. The machine failed due to a power outage or to overheating. So I see that this is an or statement here. Our P being that it failed due to a power outage, our Q being that it failed due to overheating. And then we're told that the machine has a working backup generator. Now this one I'm trying to be a little tricky with, because that does not match the exact wording there of P or Q. However, we can also kind of use some reasoning here that if it has a working backup generator, then it would make sense that the power would not go out, right? So it appears that there is power, which means that not P is true, right? So it did not fail due to a power outage. And so if you remember, in the case like this, we have P or Q and not P as our premises, then what we can conclude is Q, which is that the machine failed due to power outage. Okay. So those are two examples of valid arguments. And sorry, I forgot to write. The second one here is the law of disjunctive syllogism. Okay. So let's look at fallacies now. And these fallacies is kind of a fancy word for invalid arguments. Or they're arguments that lead to an error in reasoning. So the first that we're going to look at here is the fallacy of the converse. And again, as we go through these, keep in mind that these are invalid arguments. So again, we'll start with the symbolic representation. So we're given that P implies Q is true, and also that Q is true. And in these cases, even though these are fallacies or invalid arguments, we assume there that those two parts are true. And then where the fallacy or the error comes in is that the conclusion is a problem. So here we conclude that P must be true, okay? And as we'll see, that doesn't work. So let's look at an example. over here on the right. So if the battery is dead, then the car won't start. So this is a conditional. It's a P implies Q, P being the battery is dead, Q being the car won't start. And here we're given that the car won't start. So the second part of that. So therefore we conclude P that the battery is dead. And if we think about why that's an invalid argument, right? Any of us who have cars can perhaps suss this out, right? Just because the car won't start, that doesn't necessarily mean that the reason for that is that the battery is dead, right? We're told up here that if the battery is dead, then the car certainly won't start, right? But it doesn't necessarily mean that the only reason the car won't start is because the battery is dead. So that was an improper conclusion for us to make there. All right, a couple of more examples. The next one is the fallacy of the inverse. And so again, starting with the symbolic representation here, we're given that P implies Q is true, and also that not P is true, excuse me. And so therefore we conclude not Q is true, okay? And if you think about why this is, symbolically, we're told that the conditional is true, and then we're concluding, more or less, that not P implies not Q. But if you remember, the conditional does not have the same truth values as the inverse, right? It has the same truth values as the contrapositive, but not the inverse. So that's why this is a problem. So let's look at an example of this. So here we say that if you drive fast, then you will arrive early. So we see we have our P implies Q. We say you did not drive fast, so not P. And so then we conclude, therefore, you did not arrive early. So we assume or conclude not Q is true. But if we zoom out on this, okay, let's think about this. They're telling us that for sure if we drive fast, then we'll arrive early, okay, and then that we did not drive fast, all right? And this is kind of similar to the previous one that, that doesn't necessarily mean that we will not arrive early, right? We could, on our way to wherever we're going, get lucky and all the stoplights are green, or maybe traffic patterns are different, and so we're just able to get to our destination faster. It doesn't necessarily guarantee that we will not arrive early, right? We're told that if we drive fast, then we will certainly arrive early, but it doesn't tell us what happens if we do not drive fast. Therefore, we can't conclude that we won't arrive early. All right, and the last one of these is the fallacy of the inclusive or. This one is really interesting because it shows the difference between or in math and or in kind of our common language. So this one again has two forms, and you'll see that they're both very similar except for a letter. So in both, we're told that P or Q is true, and then we either assume P is true or Q is true, and then the issue is that we conclude that not Q is true or not P is true, or in other words, that Q is not true or P is not true. Okay. And so the example here is that Jason will take psychology or sociology. So P being that he takes psychology, Q being that he takes sociology. And then we are told that Jason takes psychology. So we assume then not Q, or conclude then not Q, or that Jason did not take sociology. Okay. And again, this one is not true because of the differences between what or means in math and what or means in our common language. So if I said to you that you take psychology or sociology, you might think we mean one or the other. But when it comes to math, that's not necessarily the case. Because remember, if for an or statement to be true, the first part can be true, the second part can be true, or both parts can be true, right? And so it could be true that Jason also takes sociology. We don't know. So we can't just conclude that he didn't. All right, to wrap up here, let's take a look at some examples of these and see if we can figure out what types of fallacies these are. So this first one, the premise is if you listen to Taylor Swift's new album, then you are a huge fan of T Swift. And just so you know, for the those who are ignorant of this, T Swift is the same person as Taylor Swift. So here I see that we're given that P implies Q, so a conditional is true. And then we say you didn't listen to Taylor Swift's new album, so it looks like that's not P, and therefore we can conclude not Q, right? And again, this is an error in reasoning, right? Just because you didn't listen to the new album doesn't mean you're not a huge fan. Maybe you just didn't have time yet. And so if we look back at our list, right, this is an example of the fallacy of the inverse, right? So just because the conditional was true and then we're told the first part of the conditional is not true does not mean we can conclude that the inverse is true or that the second part of the conditional is false in this case. All right, and then our last example for right now. If I drink coffee afternoon, then I have a hard time falling asleep that night. So again, we have a P implies Q. I had a hard time falling asleep last night, so Q is true. And so we conclude I drank coffee afternoon. So we conclude P. All right, so again, we told the conditional is true and the second part of the conditional is true. So we assume the first part is true. But again, that doesn't necessarily make sense, right? There could be other reasons we had a hard time falling asleep. Again, we're told that drinking coffee definitely makes us have a hard time falling asleep, but doesn't say that that's the only thing that does. And so this is, we're again assuming, given that the conditional is true, that the converse is true also this time. So this is the fallacy of the converse. Okay. All right. That is it for now. So I thank you all for watching and take care.